Ivan will have the talk about gaming, game programming in Go. Ivan is one of my colleagues at Develer, and he's very passionate about game programming. So now listen to his talk. Let's start.
Do you hear me? Yeah. Okay, perfect. So what we will talk about today. Basically, this will be just an overall overview of how a multiplayer game server is developed. And I want to share with you an experience in developing a game in a team, very small team, and in very tight timings, deadlines, because it was a game developed for our Develer internal challenge, which basically was 3 months, and not 3 months of full time, but just 3 months of spare time game development. So it was a perfect test bed for Go, I think, but also a perfect occasion just to pick up a right technology and try to fit it and make it work in less time possible and hopefully less bugs possible. But let's have like a quick overview about the difference between game servers and their web counterparts. Because basically, I think most of you are used to web programming, at least at some degree. And we will see that game servers have really few things in common with web servers. And let's see why. First thing is stateful versus stateless. I think that everybody here knows what HTTP is and how it works. What we basically have is independent requests. And this means that all of our requests perform in like independent context, no context at all, I think. We have cookies for that, and everybody knows about cookies, so that's not the most like elegant solution to this. But a typical www server or HTTP server is something which handles, even like for the same user, handles the requests as if they were completely independent. This means that we have no state. The state is kept either on the server or partially shared on the client side. But we have like nothing which tells us that one request is coming after another and they just communicate to the same thing. Next part of this is vice versa. Games are all about state. Think like of your preferred game. I don't know, that could be whether a first-person shooter, a mass multiplayer game, even like a chess game or a card game, but in online, like multiplayer. We have like a state which defines what our game world looks like. So we need like to transmit this state across the network, and we have to do that in a way which ensures state consistency. So all the clients, players, if you want, have to be connected and have to share the same state in order to represent the world like in the same way for everyone. It will be like very ugly if like playing a first-person shooter you see people flying and so on, because that's not how it works. They have to be valid. I mean, the data which is in the state has to be consistent with the game rules. So it's not something which breaks the game mechanics and so on. For example, if you have like a cheater, so somebody who says that his state is about having like more hit points than necessary, that means that the state is consistent across everyone, but it's invalid. And synchronization is the core concept, which is very different from what we have like in HTTP and web servers in general, because it happens that since we are playing a game, we want to change the state in some way. This is performed by requests to the server. Depending on the model we choose, there are something like games which are peer-to-peer. And that happens like to be a completely different domain, but we won't be talking about this today. So keep in mind these three concepts, and let's see how we can achieve them and how we can ensure that everything plays well and the game is fun to play. So, as said, game servers hold the state and manage the state. So it's the common domain, like for this, is to have an authoritative game server. So there is one entity which decides that for our game, we have this entity which we trust and has the authority to change and impose, like force the state. clients usually are just dummy renderers in a perfect world. We will see that that's a bit different in real world, but clients usually should just have one task, one job, which is to render the state which it was communicated by the server. Also, another different thing is that in games, multiplayer games, in order to achieve some features which are very of big value to players, we can share just a partial state to the clients in order to have like prevention of cheating, fog of war. I mean, let's say we are playing a strategy game, right? So we want like to share just the part of the state in order to let the client render only the part which is of his interest. This means that you don't have to share the whole state in order, because if the player has access to game code, and this is especially like true for open source games, but even like very, I mean, guru programmers which can do assembly things and so on, like you cannot really trust the client. So the only way you can ensure that nobody cheats and sees your cities across this virtual world, you have to share just a part of state to it. And that even complicates more the things. So for web, we have HTTP. For games, we have nothing, because every game is different. So every game defines the concept of state. For my world, which will be like a strategy game or a first-person shooter, I have a completely different state. In one, I have like entities. In other, I have like armies of archers and, let's say, swordsmen, whatever. Obviously, web is based all about interoperability. So we have like browsers which talk the same protocols, and this basically is not needed at all for games. And we don't like need to implement anything like this. At least this is the funniest part about it. As said, the game defines the state and the protocol, obviously. Two core concepts, latency and bandwidth. For this, I mean, everybody likes to blame, I think, the designer which puts all those 200 and something x 200 and something images on the front end, which takes a lot to load. But that's acceptable because you have no real strict requirements on what is actually transmitted over the wire and the timing about that, because it's acceptable even to wait like for a few seconds for a big site to load, like YouTube or, I don't know, your mail account with huge images and so on. For games, this just don't work. I mean, what we are interested in is lowering both, and obviously for a smooth gameplay, in order to like play well, we have to reduce a lot the latency, but that I think we cannot play too much on that, because that depends on the connection the user has, the player, and the bandwidth, what we transmit over the wire. So I think all of you are at some degree familiar with what TCP and UDP are, and that's the only thing we have, and probably we should base our protocol on top of that, because it's common, it's supported across all the clients, like mobile, web, operating systems of all kinds support them, and we have to use them. But which one? So let's see just a few examples of that. I will start with my favorite, Quake. Who have played Quake here? Okay, pretty good. Okay, so what is Quake? It's a first-person shooter in which the player task is to blow the head of the opponents. So that's just the basic gameplay. But what we know is that in order to play this game well over the wire, so a network game, we have to do a lot of tricks in order to keep this lot of state changes, because if I click like on my mouse or whatever controller I'm using, I want to deliver like the rocket into the head of that guy as quickly as possible, and to notice no delay in that. So because probably if anybody of you like played Quake or some other game on a very shitty connection, I mean, it noticed like that you shoot at someone, but he's the next frame already a few meters away, so you miss him. We want to avoid this. So in order to do that, we have to use prediction and interpolation. So what I have, like states sent in a bunch, really a lot of states sent over UDP. So we have no guarantee of the order. We have no guarantee of the delivery, actually. It could be like a black hole in which all the packets end. And we have to use few tricks on the client side in order to deliver a smooth and very like enjoyable game experience. So that's how Quake works. High frequency state changes and UDP for the network protocol. Everybody knows this game, right? Okay, maybe I think that I have passed too many hours there, but at least the thing to say about this one is it's a good mixture of TCP and UDP, and we will see why. So basically what we have is player actions, which could be like casting a charm, or I don't know, pick up something like loot a cadaver, or transmit commands to the team and so on. So these are changes we would like to deliver as soon as possible and to see them applied. But those are so important and so infrequent that we can use TCP for that. So we have the cost of the full round trip, but the game like uses few tricks to user and to make him feel like if it was a real-time action. So for example, if you cast a spell, the client immediately starts to render the magic, the effects, and so on. But if you notice sometimes, if you have a laggish connection, the monster dies not immediately. It dies just half a second later, depends on your connection. That's why, because client took it for granted, like that the packet was delivered in time, and the action had place. So he renders a finished action. But since the server is the authoritative entity, he must wait in order like to show the animation of the monster exploding and so on. Actually, World of Warcraft is a very polite game, so nothing explodes there. But in order to show the animations and like experience gain or health bar changes, we must like receive for the NAC from the server. That's why it's good mixture of TCP for those critical actions and UDP for seeing like rotations of the monsters, because we want like to see that more monsters are facing us when they attack us, or vice versa when we like use the bow to kill somebody from distance. We want like the things to play well correctly and see the animations which are fit very well together. This one is a third example. Everybody knows it, right? Good. That's actually very much better to dedicate thousands of hours on this game than on that one. But what we have here like is a strategy game, turn-based strategy game for those who don't know about this. And the point here is that since we have turns, we have to deliver something like a consistent state. So the state in this game is our world, the nations, the units, the money each player has, I don't know, the diplomatic pacts he has, and so on. So it's a very like bloated state. We have an overall overview of the game world, and this must ensure that we see every part of it. So the states can be really huge in payload. But we have like a stream of actions which is very small. So like moving few units for turn or choosing the production of a city is just few bytes of things, and we can use just TCP for that. We don't need like high frequency submission of data to be delivered and accepted and acknowledged and so on. So these are three examples, and later I will talk like about our game we developed for this contest and which solution we pick and how Go helped us with that. But let's just talk a bit more about one aspect which is usually overseen in this domain of game server development. So what should we do with security thingy? Well, do it yourself. So basically, for this part, there are very few libraries and definitely very few Go libraries. But one should ask himself, is it really needed? So if you are playing a first-person shooter and somebody comes performs a man-in-the-middle attack, the worst thing you can see is that somebody takes control of your character and shoots somebody in the head. Well, that's, protecting your channel, encryption, whatever you have to throw it in, it's really not of that value for a game which is of kind of like first-person shooter strategy and so on. But if you have a thing which is microtransactions or in-game buying of things, so suppose you are implementing a freemium model of games, so where you play for free, but what you need later is that, okay, I'm stuck with playing with this character, I just want to pay a few bucks and want to pick the most powerful weapon I have. So you should think of a way to implement it in-game, but if you can just offload it to the most traditional web. So everybody probably seen these game launchers, which open just a small browser view into the launcher. And you can do your login, authorization, authentication stuff. You can use your credit card safely because you have all the power of traditional web, like the stack of SSL, OpenTLS, and whatever it is. So in case, I won't talk about security anymore, but just if you are going to implement something, think twice, do you really need it? So I will introduce the game we developed. Develer, it's not a typo. It's a word game about this team of developers which try to survive a zombie apocalypse in the office of Develer. So what it is, basically, don't look the ugly graphics because it was a 3-month challenge and I'm to be blamed for it. But what do we have here? So basically, it's a cooperative role-playing game. What we have to do here is join in this party, which is a lot of engineers, programmers, the security guy there, and they will have just one task, is to kill zombies. Actually, zombies are styled like hipsters, and I think everybody wanted to kill a hipster in his life. So right now you can. And basically, the target for this game was a LAN party. When you are tired at work, you can just detach and play over the wire in this kind of self-contained missions. There is a lot of stuff to do, but we are working on it. So, and we had to develop this thingy in 3 months. We chose Go for the server, and the following part of the talk will be about reasons why we did so. So, what we have here, many players joining with different characters. We have a common level in which everybody plays. We have these zombie entities, which are artificial intelligence entities, so nothing which really is controllable. Their basic desire is to eat your brain, so I don't think there is too much logic in a zombie, and nobody expects it. And we will see the engineering choose which we do for few of the technologies here. So we chose TCP because it's a role-playing game, and we felt quite good at the rate of submission of data, because commands like to kill a zombie or loot something or use the coffee machine, as the guy here does. Actually, programmers live on coffee, so that's why his life is refilled with coffee. And basically, all of this is defining a low-pace game. So it's something which is taking place, even if it looks for one player, actually looks very annoying, and also boring. But when you have a lot of players, even if to a human, it looks like a very dynamic game. In reality, it's just something which has one action every 2 or 3 seconds, something like that. So we don't really need to send a lot of stuff. And actually, client does a lot of interpolation here. So when, for example, I give the grunt a command to go and kick the zombie, it just delivers one packet to the server. Go and kill the zombie at that coordinates there. So everything else is done on the server. And since the client received an ACK through the TCP, the client can go further and interpolate everything and say, OK, I'm able to do this animation. I'm doing that. I'm, let's say, changing the health bar because the server answers each time with the full game state of the world. And let's go for the actual code. What we have on a typical game server, actually this game server. So we have a network layer, game state, which is this macro entity which contains our world, the definition of everything which has place in it. And we have artificial intelligence and logic, not so much intelligence, but a lot of logic, and game data, which basically is shared and we will see a bit later. And this like main loop, which ties everything together. And let's start from the most interesting part for me, which is network. So this is where Go really excels at. Basically, we had to use no external libraries except for the message pack thingy, because our game state is encoded in message pack. But it felt like really pleasant to develop using Go, because I'm not sure if anybody tried to develop a network server in C. Anybody tried? At least some application in C, or we have one there. Well, basically, you have like to use sockets to define everything by yourself, use foreign libraries. If you are trying to playing a cross-platform, that's a hell, because Windows has a different concept of Unix sockets, and you have to use one additional library for that. And everything like serialization, encoding, and so on is a hell. So you have to put together all these libraries, and you are spending most of your time just doing that. I mean, integrating, compiling libraries into your build system and trying to let them work together. Go has this killer feature as for me, which is reader and writer interfaces, and those just do everything. You throw one piece of data through it, being it encoded through message pack, which obviously supports these interfaces, and go ahead with that. Even if it was a 3-month challenge, we had so much time that we implemented even a telnet port for administration of the game. So one did just basically log it in and, let's say, created a few zombies by hand, orchestrated scenarios, and so on, or kicked a player. What about game data? This basically is the resource, which, I mean, the level you have seen there, the entities, the number of hit points of the zombie, the number of, the strength of a programmer or engineer or the grunt entity. So all this is defined in JSON files. Why JSON? Because, well, it's very well supported across languages, and we have no real way to invent something ours. I don't think it's really meaningful to do. And obviously, just to packages, OS and I/O. I mean, with everything this, contained in Go standard library, we just did most of the things for languages like Java and C, C++. You have to either write by yourself or use foreign libraries, which really doesn't pay off. And this is probably the part which required most work to do, because we had found that basically a lot of code is to be written by yourself. So there is if anybody of you is interested in game development, probably you heard about physics. Libraries such like Unity, I don't know, a lot of tools which are used to do game development. They can really help you because they have a lot of math inside implemented, especially for physics. We didn't really found, with my team, anything which feels stable, mature, workable in Go. So for physics, we just used a very plain math library and implemented on top of it something ours. And the very difficult part was the pathfinding. The game you will see on GitHub, actually it's available as open source. So, I mean, for real piece codes, you can just go there and pick it up. So pathfinding was something we'd have to port like a C++ library and use part of it in order to have something good looking and working. And the game state. What is the game state? It's basically which we need to put over the wire. It's something which also the server internally have to change with all the clients and performing their requests to change it and have serialize it, deserialize, and that's where Go really plays well because it has the reflect package, introspection features, and this allows just to put your whole structure, whatever it is, and dump it to message pack encoder. That's a thing which felt so natural to do in Go, and especially try to think about how would you implement that in C++. Everybody worked with Qt, actually have variants, all of those serialized, deserialized methods which you have to implement for every type of data and so on. You have to put pieces together which are completely heterogeneous, but they must work together. So you end up in your camera class supporting serialization interface. Why? And that's the point. So you have everything out of the box in Go. And we are going to the core and last thingy, which is the main loop. How Go plays well with this? Actually, for all of our systems on the server, I'm talking about the server, we have like Go routines. Client registration, data serialization, reading and writing, whatever it is, there is a Go routine for it. Obviously, to synchronize them, you have to use channels. I will suggest for those who are new to Go to really make theirs these concepts of channels and the Go routines, because they are a killer feature. I mean, making asynchronous, or let's talk a bit better, concurrent code is really a cake with Go, because you have it as part of the language. You have this thin runtime which does everything, and basically you are off with it. One thing which you needed to do is the generation of few type and, let's say, definitions for containers and so on. And there, obviously, somebody will say, oh, why Go doesn't have generics? I think it doesn't have to, because there is like this excellent built-in generation of code. And you have like your explicit structures, which are generated and compile at time, and you are using it if they were part of your library, but you haven't written them. So give it a try to Go generate and go with that. So basically, I mean, just to recap very quickly why we choose Go and what really paid off for us is obviously the standard library. I think that no language, even Python, has a lot of this stuff. Actually has it more, but it's a slower language, much slower. If you want to implement a multiplayer game in it, you will end up like in tons of server farm thingies, because you will need to run it very quickly. We have Go Compiled, which is fast. Introspection, which is part for the serialization, which really pays off, and concurrent code. And also good principles, like the compiler, which yells at you if you try to put that brace on the new line, for example. So this is, this crazy guys is the team which worked on this, and all the code is available there. So if you really want to pick it up, actually we are open to any kind of collaboration. So it's an open source game, and the point there is maybe at some point it will be released on Steam, but the point there is we will sell just the assets, so nothing really serious. And you can pick up all the server, all the client, renderer, whatever we implemented for the game, you can pick it up at the GitHub repository. That's it.
Well, thank you, Ivan. And if someone wants to ask something to Ivan, I'll wait for the mic.
From what I understood, you have used the Go language on the server side, but also on the client side, or
no,
you used
on client it was just in Python. And the reason for that is that actually Go was a language we were starting to learn. And Python is a language we knew very well, and especially because it provided very fast wrappers around C. So our renderer, based on OpenGL, was written in C. So we need like a language which was fast enough on one machine, which Python works very well for, has a good standard library because of the tight requirements of the challenge, and plays well with other languages. So for network, it has JSON, message pack, whatever you need, and it has convenient wrappers like fast foreign interface for C.
But the connection between client and server, it was just plain TCP sockets?
Yes.
Okay.
Yes. TCP sockets, and the datagrams of the state was binary message pack. That's it.
Anyone else?
And have you considered protobuf or flat buffers for instead of message pack?
Yes, actually, we were trying. I mean, most of the solutions we adopted were driven by the desire to keep it simple and as fast as possible. Protobufs are probably have like even better compression ratio for the binary data. But the point is that since it's a role-playing game, I think that we had something like 1/10 of a second rate of submission of the full payload. It turned out to play very well for a LAN network, So maybe if we are going, and we are going for the internet, we probably will choose something like protobuf.
And so it was mostly because you already knew MessagePack?
Yes, actually, because everything was like the basic data structures and data was in JSON, and MessagePack feels like the binary JSON, you know. So the reason for that was that it also was like really easily to print out and have like tools for formatting. So for debugging reasons, there is a telnet command which dumps all the state, and that turned out to be quite convenient. But that's the only reason. There is no argument against protobuf or others.
Okay, thank you.
What did you find the most difficult part, or maybe the biggest weakness of Go when it came to writing the game server?
Lack of libraries for the logic part. I mean, it's a very good language for the whole infrastructure, organizing the code, going parallel and so on. But it's a bit young considered to others. And you basically end up in either writing yourself the, let's say, code which does artificial intelligence, if we can call it, but it's not really. But especially for math. I mean, Go core package is just basic math functions. You don't have linear algebra, matrix algebra, and so on. You have a few libraries, yeah. But for example, I just was looking yesterday at the list of them. 2 are not maintained, and 1 is really just about matrices. You don't have like anything like physics, especially like wrappers for Chipmunk libraries and a few others. But the point that we wanted like to keep the server with less dependencies possible on compilable code like C and so on. Right. So like it's a game which is on a flat level. So the only thing you need is 2D collisions, which are basically done by circles. So just doing few equations is the simplest way to go instead of wrapping like full future library like ODE or physics. That's basically just the reason. But everything else, like the part we lost most time in was logic. The part I think time we gained by using network and I/O facilities of Go was just months, maybe more.
Great, thank you.
That's it. Nobody else?
Nobody
Actually,
else?
I'm available all the time today. So just if you are interested in whatever, or even joining us, yeah, you can ping me. Thank you.
Thank you, Ivan.